The sky is not blue because it's reflecting the ocean. That's a myth you were probably taught in third grade, and it's completely wrong. The real physics behind why the sky is blue, why sunsets turn blood red, why the sky isn't actually violet even though it should be, and why astronauts see a pitch-black sky at noon. By the end, you'll never look up the same way again. Let's start by burying that reflection myth for good. If the sky were blue because it reflected the ocean, then landlocked deserts with zero water for 1,000 miles would have colorless white skies. They don't. Antarctica, the driest place on Earth, has a sky just as blue as Hawaii's. The ocean is actually blue for a completely separate reason. It absorbs red light and reflects blue back at you. Two totally different phenomena that just happen to share a color. The real answer to our mystery is hiding somewhere much smaller than an ocean. It's hiding in the air itself. Here's the setup. Sunlight looks white, but it's actually a mixture of every color of the rainbow, all traveling together in waves. Each color has a different wavelength. Red light stretches out long and lazy, around 700 nanometers. Violet light is scrunched up tight, around 400 nanometers, nearly half the size. Now, Earth's atmosphere is packed with tiny gas molecules, mostly nitrogen and oxygen, each 1,000th of times smaller than the wavelength of visible light. When sunlight slams into one of these molecules, something strange happens. The light doesn't just pass through. It gets absorbed for an instant and then re-emitted in a random direction. Scientists call this Rayleigh scattering, named after the British physicist Lord Rayleigh, who worked out the math in 1871. And here's the part that changes everything. This scattering effect is not equal for every color. Rayleigh's equation showed that the amount of scattering is proportional to the inverse fourth power of the wavelength. That sounds like a mouthful, so let's translate it into something you can actually picture. Shorter wavelengths scatter dramatically more than longer ones. Specifically, because blue light has a shorter wavelength than red light, blue light gets scattered around 5.5 times more often than red light. Violet, being even shorter than blue, should scatter even more, about 9 times more than red. So when sunlight enters the atmosphere, red, orange, and yellow light mostly punch straight through undisturbed, heading toward the ground in a fairly straight line. But blue and violet light ricochet off nitrogen and oxygen molecules over and over, bouncing in every direction across the sky. That scattered light is what reaches your eyes when you look up. Not from the direction of the sun, but from every direction at once. That's why the whole sky glows blue, not just the spot where the sun sits. But wait, if violet light scatters even more than blue, shouldn't the sky be violet, not blue? This is the question that stumps most people who think they already know the answer, and it's where the real science gets interesting. 3 things save us from a violet sky. First, the sun emits less violet light than blue light to begin with. The sun's output curve simply favors blue. Second, our upper atmosphere absorbs a chunk of violet light before it ever reaches scattering altitude. And third, this is the big one. Your eyes are the deciding factor. The human retina has 3 types of cone cells for color. One's tuned to red, green, and blue wavelengths. Violet light lands right at the edge of what your blue cones can detect, so it actually stimulates both your blue and red cones slightly. Your brain takes that mixed signal and blends it into what you perceive as blue with a faint violet undertone. In other words, the sky isn't just a physics problem. It's also a biology problem happening inside your own skull. Here's a detail almost nobody mentions. The blue you see directly overhead at noon is actually a slightly deeper, richer blue than the pale blue near the horizon. Why? Distance and layering. When you look straight up, you're looking through the thinnest possible slice of atmosphere. Sunlight only has to travel through one layer of air before scattering into your eyes, so you get a purer concentration of scattered blue light. But when you look toward the horizon, you're looking through a much longer, thicker path of air, sometimes 20 to 30 times more atmosphere. All that extra distance means the blue light scatters so many times it starts to scatter itself into randomness, washing out and mixing with other wavelengths. The result is a paler, almost whitish blue near the horizon line. Same phenomenon, different amount of atmosphere to travel through. Now here's where it gets genuinely dramatic, because the very same physics that paints the sky blue is what paints a sunset fire engine red. During the day, sunlight takes a short, direct path through the atmosphere to reach you, straight down through roughly 1 atmosphere's worth of air. But at sunrise and sunset, the sun sits low on the horizon, and its light has to travel through the atmosphere at a steep sideways angle. That path can be up to 40 times longer than at noon. Remember the fourth power rule? Over that much longer path, almost all the blue and violet light gets scattered away long before it reaches your eyes, scattered off in every other direction, illuminating the sky elsewhere, anywhere but straight at you. By the time that light reaches your eyeballs, the short wavelengths have essentially been filtered out entirely. What survives the journey is the light that scatters the least, the long, lazy wavelengths of orange and red. So a sunset isn't some separate phenomenon needing its own explanation. It's the exact same Rayleigh scattering, just viewed through 40 times more air, which strips away every color except the reds and oranges tough enough to survive the trip. Here's a fact that surprises almost everyone. Some of history's most spectacular sunsets were caused by disaster. After the 1883 eruption of Krakatoa, sunsets around the entire planet turned an unnatural glowing red for nearly 3 years. Fine volcanic ash and sulfate particles were flung into the upper atmosphere, adding extra scattering particles into the mix. Particles larger than gas molecules, which scatter light differently through a related process called misconception. The result was sunsets so vivid that fire brigades in New York and London were called out because people thought the sky was literally burning. The same thing happens on a smaller scale with air pollution and desert dust today. More particles in the air means more scattering, which often means richer, deeper sunset colors over polluted cities. A strange twist where something harmful produces something beautiful. Want proof this is real physics and not some Earth-only coincidence? Look at Mars. Mars has almost no nitrogen or oxygen. Its atmosphere is over 95% carbon dioxide, and it's incredibly thin, less than 1% the density of Earth's. But it's full of fine reddish dust suspended constantly in the air. That dust scatters light completely differently than gas molecules do. Larger dust particles scatter red and orange light around more effectively than blue light, almost the reverse of Earth's gas-driven Rayleigh scattering. The result: Mars has a butterscotch tan-colored sky during the day. But at sunset the roles flip. The dust that scattered red light away all day suddenly lets blue light punch through along that long, low sunset path, giving Mars genuinely blue sunsets, captured on camera by NASA's rovers. Same underlying physics, completely different palette because the ingredients in the air changed. One more piece completes the puzzle. Astronauts on the moon, in full blazing sunlight, look up and see a completely black sky, even with the sun directly overhead. Why doesn't the moon have a blue sky too? Because the moon has essentially no atmosphere. No nitrogen, no oxygen, no gas molecules to scatter sunlight in every direction. Without something for light to bounce off of, there's nothing to spread that blue light across the sky. Light either heads straight at your eyes from the sun, or it heads off into empty space and never comes back. There's no in-between, no glow, no scattering, no color. Just black. This is genuinely elegant proof of everything we've covered. No atmosphere, no scattering, no blue sky. Give a planet or moon an atmosphere, and you switch the blue sky back on. So let's run it back in 20 seconds. Sunlight contains every color. Tiny gas molecules in our atmosphere scatter short wavelengths. Blue and violet, far more than long wavelengths like red. Your eyes interpret that scattered blue-violet mix as sky blue. At sunset, sunlight travels through dramatically more atmosphere, scattering away almost all the blue before it reaches you, leaving only red and orange survivors. Change the atmosphere, like on Mars or the moon, and you get an entirely different sky. One elegant rule of physics, discovered in 1871, quietly running the show above your head every single day of your life. Next time you glance up on a clear afternoon, you're not just seeing blue. You're seeing billions of nitrogen molecules flinging sunlight in every direction at that exact instant, just for you. And tonight, when the sun dips low and the sky turns orange and red, you'll know exactly why. It's the same light, taking the long way home.